In case you find this video helpful, please subscribe to my channel for more. Welcome to this lesson. Let us look at this question, a titration question. This is paper 3, a practice. You are provided with dilute hydrochloric acid, solution A, 0.1 molar sodium hydroxide, solution B, 10 grams of a mixture of sodium hydrogen carbonate and sodium chloride per liter, solution C. So I want first to explain 10 grams of the mixture per liter. So this mixture, the total mass that was dissolved to form at 1000 centimeters cube is 10 grams in 1 liter. Very important. 0.1 molar simply means that this is the number 0.1 capital M. Capital M stands for molarity. So therefore this is the number of moles in 1000 centimeters cube of solution B. Very important to note. You are required to determine the molarity of solution A, the percentage purity of by mass of sodium hydrogen carbonate. Procedure: fill the purate with solution A. Pipette 25 centimeters cube of 0.1 molar sodium hydroxide solution B into a clean conical flask. Add 2 drops of methyl orange indicator and titrate with solution A until a permanent pink color occurs. Fill in the table below and repeat. Therefore, it is important to understand which solution is in the purate. So we are putting solution B, 0.1 molar in the so in the purate we are going to have solution A. Remember, solution A is HCl. Then we are going to pipette 25 of B, sodium hydroxide. This information is important to understand it. So let us take some values and then we shall use them to calculate the questions that follow. So our table is complete. So make sure the table is complete. You have used 1 decimal place consistently. You must use 1 decimal or 2 decimal place consistent. The arithmetic, subtracting 20 minus 0 is 20.0. 20.5 minus 0 is 20.5. Therefore, the arithmetic mark you should get. For you to get all these marks, 4 of them, you have to make sure the table is complete. Decimal point is correctly used. And then the arithmetic, the subtraction is correctly done. So let us do the average. Now you see this is 20.5, 20.0, 20.5, and then 20.5. It means that this one is an outlier. The decimal point is less when you compare. So we are going to do the average with these two. It is important to know. So even if you do with 3, there's no problem. But for accuracy, you need to do with those that are very close. For now, let us use 20.5. So average is 20.5 plus 20.5. If I decide to use only 2, I'm going to divide by 2. But let us use 3. There's no problem. Divide by 3. This one will give us 20.33 centimeters cube. Calculate the number of moles of hydrochloric acid solution A that reacted with 25 centimeters cube sodium hydroxide solution B. Remember, from what we were given, there is no information we know. We don't know anything about solution A. We only know that solution B, sodium hydroxide, has got a molarity of this. And now we have the volume of solution B and the solution A. Therefore, it is important to understand that for us to get the number of moles of solution A, first we must have the number of moles of solution B, because now we have 2 information of solution B. We know very well that 0.1 capital M is the number of moles. This actually means that is the number of 0.1 is the number of moles which are in 1,000 centimeters cube solution B. The volume of solution B that we used is 25. Remember that? 25 centimeters cube of B. Therefore, we will ask 25 centimeters cube B would contain how many moles? Therefore, it is 25 times 0.1. We divide by 1,000, and our answer is 0.0025 moles. So this is the number of moles of sodium hydroxide, but the question is not asking number of moles of sodium hydroxide. So how can we get the number of moles of hydrochloric acid? Remember, A reacted with B to give us the product. We know A is HCl plus B is sodium hydroxide. They react to give us sodium chloride plus water. We know the ratio here is 1 to 1. It means that the number of moles of 25 centimeters cube solution B will be equal to the number of moles of hydrochloric acid, because the mole ratio is 1 to 1. Mole ratio. Now, since mole ratio is 1 to 1, moles of A used is 0.0025 moles, the number of moles, because the ratio is 1 to 1. So it is important to understand that. Question C. Calculate the concentration of solution A in moles per liter. Moles per liter simply means molarity. What is molarity? Molarity is the number of moles of a solution in 1 liter in 1,000 centimeters cube. So whenever you are being asked concentration in moles per liter, simply means molarity, because this is the number of moles in 1 liter, and molarity is the number of moles in 1 liter. Therefore, concentration in moles per liter simply means molarity. Now we have the number of moles of solution A of the volume we used. Our volume was solution A used is A is 20.33 centimeters cube. So we know that the number 0.0025 is the number of moles of A in 20.33 centimeters cube. That is the volume that reacted with 25 solution B. But the question is asking us to calculate molarity of A. Molarity, or concentration in moles per liter, we want to find the moles in 1,000 centimeters cube. So we will ask 1,000 centimeters cube will contain how many moles? Therefore, 1,000, the question is here, so we are going this way, times 0.0025. We divide by 20.33, and this one gives us 0.12297. Capital M stands for molarity. Let us look at procedure 2. Procedure 2, pipette 25 centimeters cube of solution C into a conical flask. Titrate with solution A using 3 drops of methyl orange indicator. Record your results in the table below. So I have recorded the result in the table. I have done the average to save time. So let us go straight to question B. Write an ionic equation for the reaction taking place between solution A and mixture C. So let us look at what we were provided with. What was C? C is a solution made by sodium hydrogen carbonate and sodium chloride, right? Therefore, A, which is hydrochloric acid, will react with sodium hydrogen carbonate and not sodium chloride. So in this mixture, the HCl solution A will react only with sodium hydrogen carbonate, because this one is a base and this one is a salt. A salt cannot react with an acid. Therefore, you need to understand that. It will help you to write the expected equation. Therefore, we are going to react sodium hydrogen carbonate plus solution A, which is HCl. This one gives us sodium chloride plus water plus CO2. I think the equation is balanced. So this equation is balanced. The next thing, remember we were asked you to write ionic equation. Therefore, let us write the status. This one is AQ, aqueous. This one is aqueous. This one is liquid, and this one is a gas. I think you know how to write ionic equation. We don't write ionic equation for compounds which are in solid form, liquid form, or we don't break them. We don't break the compounds which are in liquid form and gaseous form in solid form. Only aqueous breakdown. So to make this work easier, I want to look for those ions that are here that form water and form carbon dioxide, because this one is a spectator ion, sodium, and sodium will go, chlorine and chlorine will go. So what is going to mean, so you can see, so this one is a spectator ions, chlorine is a spectator ion, so it is going to disappear. So we are going to remain with hydrogen carbonate. Remember, hydrogen carbonate is negative, right, which is aqueous, plus hydrogen ion, right, which is going to form water, which is a liquid, plus CO2, which is a gas. And this is the ionic equation, expected ionic equation. Therefore, this one is just to guide you, and this is what is expected. Writing like this in an exam is not a crime. You will do that and then write it, the correct answer down there. Number C, calculate the molarity of sodium hydrogen carbonate in moles per liter. So we can, what do we have? We know the molarity of solution A, right? We know the molarity of solution A. We have the molarity of solution A. If we have the molarity, the number of moles in 1,000, we can get the number of moles of 16, the one used. Once we get this, we will automatically get the number of moles of C that reacted with A. After that, we will calculate the concentration of C. Very correct, very nice, very easy, very simple. Thank you. Now we will ask that 1000 centimeters cube of solution A has got 0.12297 moles. Where did I get this one? We had the molarity of solution A. The molarity of solution A, we have it here. This is the number of moles in 1,000. So we will say that 1,000 centimeters cube of A is this moles. What about 16? So we will get 16 times 0.12297. We divide by 1000, and this one will give us 0.001965 moles. But remember, this is the number of moles of what? Of A that reacted with C, sodium hydrogen carbonate. That is not what we are being asked. What we are asked is the number of moles, or is the molarity of sodium hydrogen carbonate. Now we want to see the relationship between A and C. You can see the ratio, the mole ratio is 1:1. It means that the number of moles of A that reacted with B is the same. So because the ratio is mole ratio is 1:1. So moles of C is equal that reacted with A is the same, is 0.0, this one 0.19675, right? So now we have the number of moles of solution A. 25 is this one, because 25 centimeters cube solution C, reacted with A, which volume? 16. 25C reacted with the 16A. We have calculated the number of moles of 16 is this one. Since the ratio is 1 to 1, it means that the number of moles of sodium hydrogen carbonate solution C that reacted with 16A is the same, right? So this is the number of moles of 25. We will ask, what about 1000? Because we want moles per liter. Very simple. This is as simple as you can see. Even yourself, it is simple. So we are going to say that 0.0019675 moles of C, which are contained in 25 centimeters cube. So now we will find out 1000 centimeters cube will contain how many moles, right? Now it is 1000 times 0.0019675. We divide by 25, and this one will give us 0.078 0.0787 morality. We can use capital M because it is moles per liter. So now next question, Roman 2, is calculate the mass of sodium hydrogen carbonate in moles per liter. So we want the mass of sodium hydrogen carbonate in moles per liter mass. So this one I'm going to give a very good triangle here that you must always use, that says that morality RFM here is mass in grams per liter, moles per liter, carbonate in moles per liter. Is it moles per liter or grams per liter? Yeah, this one is supposed to be grams per liter. Mass in grams. Mass is measured in grams. So mass in grams per liter. So we want mass in grams per liter. So you can, from here, if you have morality, you can get mass in grams if you have the RFM. So I think something that is missing here is this one was missing. Sodium is equal 23, hydrogen is equal 1, carbon is equal 12. So from here we can get the RFM of sodium hydrogen carbonate. Sodium hydrogen carbonate, if we had sodium, everything using the relative atomic mass, we will get that the RFM is 84. The RFM of sodium hydrogen carbonate is 84. So mass in grams per liter, mass in grams per liter is equal to morality times RFM. Morality times RFM. But morality we have, morality of, remember sodium hydrogen carbonate is C, and we have the moles of the morality of C from here. Morality of sodium hydrogen carbonate moles per liter is here 0.07. So we have the morality. RFM we have here, therefore this one is 0.0787 times 84 will give us the mass in grams per liter of sodium hydrogen carbonate, and this one is 6.6 grams per liter. So only sodium hydrogen carbonate in the mixture, the mass of sodium hydrogen carbonate in the mixture, which was 10 grams, is this one, right? Now calculate the mass of sodium chloride in the mixture. Remember, this mixture is formed sodium hydrogen carbonate plus sodium chloride, and the total here is equal to 10 grams per liter. But this one, we have the mass here, therefore sodium chloride only equal to 10 minus 6.6, which is equal to 3, which is equal to 3.389. 6.61 is 1 here, which is equal to this one, grams. Right, now the next thing is, the last question is calculate the percentage purity of sodium hydrogen carbonate. The percentage purity of sodium hydrogen carbonate. So we know the mass of sodium hydrogen carbonate is 6.61. So we simply say, so percentage purity equal to mass of sodium hydrogen carbonate divided by total mass times other 100 by 100 times 100. So that is 6.61 divided by 10, the total mass, times 100, and that one gives us 66.1%. So the percentage purity for sodium hydrogen carbonate is 66.1. If you were asked the percentage purity of sodium chloride, if that is it, this one divided by 10 times 100. Thank you. We have finished the quantitative part of it. Now we are going to qualitative analysis. You are provided with solid F. Carry out the following tests and write down the observations and inferences. Place a half spatula endful of solid F in a dry test tube. Heat gently, then strongly until there is no further change. Test gas produced using a growing splint. So we are testing the gas produced using a growing splint. The observation here is this: a colorless liquid forms on the cooler sides of the test tubes. So it means that solid F is hydrated. It's called solid F is hydrated salt. It means that solid F contains water of crystallization. It contains water of crystal. So you can either write this one or this one. A colorless gas produced which rewrites a growing sprint. So we know oxygen is a gas which rewrites a growing sprint, but we are not going to write oxygen. We are going to write nitrogen, 3 ions present. Remember, you need to remember that nitrogen 1 rewrites a growing sprint, right? Nitrogen 1 rewrites a growing sprint, behaves as oxygen. Therefore, we use nitrate ions present when we are rewriting a growing sprint. Place the remaining solid in a test tube. Add 10 centimeters cube of distilled water. Shake vigorously. Divide the mixture into 3 portions. To the first portion, add 2 molar sodium hydroxide. Solution dropwise until in excess. Observation is a white PPT which dissolves in excess. So whenever we are using the reagent sodium hydroxide, dropwise a white PPT is formed, and then in excess it dissolves to form a colorless solution. What is there is what we call ZAP. ZAP is a formula like that will remind you that the zinc ions, aluminium, lead ions are present, and these are called amphoteric oxides. Those that contain amphoteric oxides, because these are the amphoteric oxides which will react with in this case they will behave as bases, as acids, and they will react with a base to form the complexes. Therefore, this one is zinc, 2 positive, aluminium, 3 positive, and lead, 2 positive present. ZAP. To the second portion, add ammonia solution dropwise until in excess. Now we are adding ammonium hydroxide solution. Then the observation is that a white precipitate is formed insoluble in excess. So if it is soluble in excess, then it means the zinc ions are present. Now that it is insoluble in excess, it means aluminum, and this one is present. So zinc 2 positive is absent, right? So if this one is absent, what is present? Lead 2 positive, aluminum 3 positive is present. This one is present and this one is absent. If it dissolves in excess, remember this one insoluble, it does not dissolve in excess. If it dissolves in excess, this one is present. Zinc is present, right? To the third portion, add 2 drops or 4 drops of sodium chloride. This one is supposed to sodium chloride. Sodium chloride. Then a white precipitate is formed. So if a white precipitate is formed, it means lead is present, right? Yeah. Lead ions are present. It means no. Is it a white or no white PPT? To the third portion, add 4 drops of sodium chloride solution. No white PPT is formed. No white PPT is formed. If there is no white precipitate formed, it means lead 2 ions is absent. And if lead ions, because lead with chloride ions, it could form lead chloride, which is a white precipitate. But now no white PPT, it means aluminum 3 positive is present. So in your exam, always choose to write what is present. But if you forget, you can write what is absent. Solid decay or liquid decay. Now we have liquid. Place about 1 spatula endful of the liquid decay in a metallic spatula, ignite it in a Bunsen burner flame. So what happens? The liquid burns with a blue smokeless flame, or burns with a blue non-smoky flame. So if that happens, then it means we have a saturated organic compound. A saturated organic compound, in this case we have alkane or alcohol. So we have R, OH or C present. So, or you can write word saturated organic compound present. You can use this or this present. To the second portion, add 3 drops of acidified potassium permanganate 7. So here the observation is that the purple potassium permanganate changes to colorless. So if it changes from purple to colorless, it means that either an alcohol is present or a double bond or a triple bond. So either this one could be present, because both of them, they decolorize purple acidified potassium manganate to color, they decolorize that. Therefore this one could be there, both of 3 of them. To about 20 meters cube of liquid decay, add 3 drops of acidified potassium dichromate 6. So we are adding potassium dichromate, which is orange. So the observation is that the orange acidified potassium dichromate 6 changes to green, right? I think here we should warm on warming. changes to green on warming. Then that one confirms that an alcohol is present. It confirms that an alcohol is present. Thank you. There are so many other qualitative and in the ring. So in the description, there are so many rings. Please use them and you will be able to benefit from this work. Thank you for watching, and I know you have learned something.
In case you find this video helpful, please subscribe to my channel for more.